Yeah, so we were just saying that we were looking at linear momentum conservation impulse, which is the integral of force, external forces. And when the integral of external forces is equal to zero, either due to the forces being zero or due to the integral being zero because the time over which you're integrating is very small. In either one of those two cases, the linear momentum can be conserved. Um, and we also looked at impulse problems or collision problems in which we have a coefficient of restitution, and we use essentially the coefficient of restitution equation in addition to momentum conservation to solve for usually two equations and two unknowns. Okay, so that's all about linear momentum conservation, and then collision. Today we're going to look at angular momentum. And the next lecture, I think we're going to do some MATLAB to do some simulations of various systems. Okay, so for angular momentum, let's start with the definition first. So imagine we have a particle P moving with some velocity Vp. It looks like I didn't draw a picture here, but let me pull up a picture. Let me show a picture in a minute. Well, I guess we'll just imagine the picture for a moment. Let me just share my screen. Okay, we have a point P. Let's say it's a point P and it's moving in some direction and its velocity is Vp. And we have some other point Q somewhere else, okay? So we have a point P moving in some direction and we have point Q that is potentially moving, potentially not moving, etc. Right? So later in the thing, I have a picture that looks like this. So later in today's lecture. So we have a point P, its velocity is in some direction. And then here I've denoted the point as O, but basically you can imagine this to be point Q, okay? Point P moving in some direction and point Q, which is potentially stationary or potentially moving. It doesn't matter, okay? So that's the picture. Let me scroll back up. So that's the setup. And then we define this quantity called angular momentum. We call this angular momentum of point P or particle P with respect to or about point Q. So it's angular momentum of particle P about point Q. And this quantity is given by or defined as angular momentum equals. So we have the linear momentum here, mass times velocity of point P. So that's the linear momentum. And then we take the cross product of the linear momentum with the position vector from Q to P. It's the position of P with respect to Q, which is basically the vector QP, okay? So if you draw a vector going from Q to P, that's this vector. And this is the cross product of that vector, position of P with respect to Q, crossed with the linear momentum, and that's called the angular momentum of that particle P with respect to point Q. For this for this definition to be true, the Q need not be fixed in an inertial frame. And this Vp is actually just velocity of point P. It's not necessarily velocity of point P relative to Q or anything like that. It's just velocity of point P in some inertial frame relative to Earth or something like that, whatever your inertial frame is, that particular problem. Okay, so that's the definition of the angular momentum. It's sometimes called the moment of momentum because like doing this cross product, some position vector times cross some vector is called taking the moments. But you're taking the moment not of forces, but of momentum. So it's sometimes called moment of momentum. I guess that's that. So that's called angular momentum. Um, and then we can take a look at what are the properties. Why do we care about this object? What are the properties of this quantity? Um, so to examine the properties of this quantity, we basically start again from F equals ma. So imagine we have this point P and there are some forces on this point P. Um, and this is the sum of all forces on the point P is going to be equal to mass times acceleration of point P. Acceleration can be written as dvp by dt, okay? So sum of all forces equals mass times dvp by dt. And then you take this equation and then pre-multiply cross product, right? So this is a vector cross product, not just a multiplication. Pre sort of do this vector cross product with rp with respect to q. That's this thing, rp with respect to q cross sum of all forces equals rp with respect to q m dvp by dt. So this is just starting from F equals ma and then taking a cross product on both sides. The equality is still preserved because you're multiplying both sides with the same quantity. The left-hand side has a name. You're all familiar with this. This is the sum of all forces, and then you're taking about at point P, and then you're taking basically the moment of these forces, right? So if you have a force, what is the moment about a particular point of that force? It's basically, if the force is applied at point P, you take the position vector of point P with respect to Q and then take the cross product with the force. That's the moment of that force. So you can call this basically the total moment about point Q. And you can denote it with sum of all moments about point Q. Any questions about that? Rohan asks, VP can be measured in any inertial frame. That's right. Yeah. Any inertial reference frame appropriate for that problem. Yeah. Like we discussed, for different problems, so there is something called the inertial frame in the universe. And for sort of Earth-bound problems, things that are just moving on the surface of the Earth, we usually use the surface of the Earth as the inertial frame. If we are doing like solar system level problems, we generally use the center of the sun as the inertial frame, or potentially the center of mass of the solar system and so on. But yeah, but the appropriate inertial frame for a particular problem is what we are measuring P with respect to. Yeah. Cool. Okay, so we have the sum of all moments basically about point Q. That's the left-hand side. The right-hand side, it turns out, is this quantity Rp with respect to Q crossed with M dVp by dt. I'm just writing that down here. And one can show that this is actually d by dt of, you're basically bringing this d by dt all the way outside. It's d by dt of Rp with respect to Q cross mvp. In other words, it's the d by dt of h, the angular momentum of P with respect to Q. And this is true if Q is fixed. Okay, this is true only if Q is fixed, it turns out. It's certainly not obvious. And the reason why is like this equality, like you can't bring this d by dt out all the way out because there are these quantities which are not necessarily constant. But it works out in this particular case. This is because, like, if you basically start out from this quantity, d by dt of Rp with respect to Q cross mvp, and then basically apply the chain rule or product rule to this, you bring the d by dt in, you go dr with p with respect to Q dt cross mvp, and then Rp with respect to Q cross m dvp by dt. M itself is a constant, so m just sort of goes along for the ride. But you get two terms here instead of just this one term. There are two terms. dr with respect to p dt is basically v p with respect to q, rp with respect to q here, vp with respect to q cross mvp, but if q is a fixed point, then this is basically vp, this is vp, so vp cross vp is going to be 0. And that's why basically this quantity is going to be equal to this quantity. And this quantity was basically the right-hand side of this equation. I sort of went over that derivation quickly, but basically the upshot of all that is the sum of all moments about that point Q of all the forces on point P is equal to the rate of change of angular momentum of the point P, of the particle P with respect to Q, if Q is fixed, okay? Any questions? So this is the equation that we're going to use, kind of. Actually, we'll use a simpler version of this equation. Does this feel like it's analogous to something? Sum of all moments equals rate of change of angular momentum. So that's this equation. Sum of all moments about point Q is rate of change of angular momentum about point Q, right? It's kind of analogous to sum of all forces equals ma, because, well, moment is kind of a force, except it's sort of an angular thing. And then on the right-hand side, ma is kind of is basically d by dt of mv. So left-hand side is sum of all forces. Right-hand side is rate of change of linear momentum. This is the angular version of that. Sum of all moments about some point q, some fixed point q, equals rate of change of angular momentum about that point q, okay? We will look at a sort of a more elaborate version of this equation maybe in 2-3 weeks, where we look at rigid body motion and so on, where you have objects that not only move in a curvilinear fashion, but also have finite extent, no longer particles, they're rigid bodies and rotate and so on. So we'll sort of talk about this equation in more detail then, or a sort of an analog of that equation then. But for now, we just have sum of all moments about point Q equals rate of change of angular momentum about point Q. Any questions? Okay. So, like we said, this is kind of like F equals ma, sum of forces equals ma. Just like we had linear impulse momentum relationship, where the integral of forces equals change in linear momentum, which is what we did last couple of lectures. We can integrate both sides. This is the integral of the sum of all moments. This is the integral of rate of change of angular momentum. Integral of d by dt, the integral of the d by dt gets canceled, and all you're left with is angular momentum from initial to final. So on the right-hand side, we have final angular momentum minus initial angular momentum of the point P, the particle P, with respect to point Q. Everything is with respect to the particular point that you care about. It's like it always has to be relative to or about a particular point. This left-hand side quantity, which is the integral of all the moments, is called the angular impulse. If you have the integral of all the forces, it's called just impulse or linear impulse. It's also sometimes called impulse integral because there's an integral there. But basically, this is the angular version of it. Integral of moments equals angular impulse, okay? So I'm just summarizing that equation again. Integral of all the impulse moments equals change in angular momentum, or in words, angular impulse integral equals change in angular momentum, okay? So all we have are these two equations so far. Sum of all moments equals rate of change of angular momentum. Well, the integral of the moments equals change in angular momentum, period. And then we had a third equation up here, which is just the definition of angular momentum. Those are the three things so far. Good to have seen the derivation, but obviously we won't ask any derivation in the exam. Looks like there's a question somewhere. What was equation 2? Yeah, so the three equations I wanted to box were basically the definition of angular momentum, contrasting with linear momentum. Basically, you take the moment of linear momentum. That's the definition of this quantity called angular momentum. And then the second equation is sum of all moments, basically of all the forces, about the point Q is rate of change of angular momentum. This is kind of the differential equation version. It's like F equals ma, right? This is analogous to F equals ma. And then the third equation is, once you integrate both sides, the integral of moments equals the change, the discrete change in angular momentum. Okay, cool. Any other questions before we try to use this equation? Okay, so like I said, this is quite analogous to the equation that we used last week, essentially, which is integral of, instead of integral of moments, you have integral of forces equals change in linear momentum. And occasionally this happens to be 0, and you have linear momentum is conserved. Okay, but this is the angular version of that. And just like last week, we can ask the question, when is this angular momentum conserved? Right, so, well, change in angular momentum is this quantity. And if this quantity happens to be 0, then of course, we have no change in angular momentum, right? So that's basically it. If the integral of moments of all the forces over a period of time equals 0, then angular momentum is conserved. This can happen a couple of different ways. It can happen if the moments are equal to 0, identically, right? So there are no moments on the system, or well, maybe there are no forces on the system, first of all. If there are no forces, there are no moments, unless there are point moments, which I guess we're not considering yet. But if there are no net moments about point Q, well, the integral of the 0 is going to be a 0. A sort of a very special case of that, it can, like just like for linear momentum balance, it can also happen that there are some finite moments, but then the time duration over which you're considering the system is really, really small, so that the integral becomes 0. That can also happen. And then in those cases, we'll say something like the time duration is very short or something like that. Okay, so in any case, so sometimes the moments are equal to 0, in which case angular momentum will be conserved because change in angular momentum is integral of moments. A very special case is the so-called central forces case. What does this mean? It means, well, basically this following example. This is the sort of most famous example. This is famous for lots of reasons, I guess, which we shall talk about perhaps at the end of this thing. But you have the Earth and you have the sun. And the sun exerts a force on the Earth. And let's say this force is called F. Well, officially, well, let me say there is something wrong with this free body diagram. What is it?
The Earth should be pulling on the sun too.
That's right. Yeah. So there's an equal and opposite force on the sun, which is like F in the opposite direction, basically minus F. That's right. So I'll fix that. But for the purposes of this sort of problem or this setting, while there in the real world, real solar system, There are other planets, Mars, Venus, I guess. There's also the moon that's relatively close to the Earth. There are other planets and satellites that also exert some force on the Earth. But for the purposes of this discussion, we are going to ignore that, okay? Ignore the forces due to other planets and ignore the fact that the sun can also move. For now, assume the sun to be fixed. These are approximations because, well, the forces are there from the other planets and the sun can move relative to the Earth and other planets in the inertial frame. But for now, we are going to assume the sun to be fixed and the forces to be from the other planets to be equal to 0. Okay, because these are approximations, whatever we are going to infer from these assumptions is going to be approximate. It's not exactly true. But it turns out these are relatively good approximations. So these are accurate to many decimal places. Okay. So super accurate, but still approximations. Okay. So if we take a look, so the sun is fixed, let's say, and sun is pulling on the Earth with some force, F. And this force is going to be toward the sun, right? It's going to be along the line joining Q and P. It's going to be along this line, okay? So let's look at what is the moment of this force about that point Q. So let's take like everything about point Q, namely the sun, namely the moments of forces about point Q, and also angular momentum of Earth about point Q. Okay, so that's what we're going to do. Moment of forces on Earth about the sun, namely point Q, is basically R. We're just going to use the formula for moments, right? So the formula for moment is just R cross F. RP with respect to Q cross F, where Q is the point about which we're taking the moment. P is the point of application of the force. This is the force itself. So that's it. RP with respect to Q. P is Earth, Q is the sun, cross F, the gravitational force. And this is going to be equal to 0 because why is this 0? I have the answer here.
Because the force passes through the point of interest.
That's right. Yeah. So that's one way to say it. That's perfectly correct. Yeah. So if you're taking moments of some force and the force passes through the point about which you're taking the moment, that's exactly right. The force has no moment about that point. Perfect answer. Another way of saying exactly the same thing is that if you take the cross product of two vectors, if they're parallel vectors, in other words, they're aligned in the same direction or sort of this way, doesn't matter. Aligned in the same direction or opposite directions. Cross product of two vectors that have basically 0 angle relative to between them is equal to 0. Okay, but absolutely, if you're taking the moment of a force about a point, it's basically force times the perpendicular distance between the force and the point. And if the force passes through that point, the perpendicular distance equals 0, right? So that's something that you guys learned from your statics and perhaps other classes. Cool. Brennan says they're parallel. That's right. Okay, so the moment is basically 0 about the sun. It's not 0 about any other point. It's 0 about the sun, just the special point, okay? Well, this means that H, namely the angular momentum of P with respect to Q, is angular momentum of Earth with respect to the sun, is conserved, right? Change in angular momentum is the integral of this quantity. So angular momentum itself is conserved. What we mean by that is before equals after, initial equals final, right? So this is sort of the famous principle, I guess, for planetary motion. The angular momentum of a planet, in this case Earth, but doesn't matter if it's Earth or some other planet, about the sun is conserved subject to these approximations, right? So this is assuming that the sun is fixed and it's the only planet around, but it turns out that the sun is the biggest sort of gravitational pull. Other planets are relatively small compared to the sun. So it turns out these approximations are pretty good. So saying that the angular momentum of a planet relative to the sun is conserved is a reasonably pretty accurate relationship. Any questions about this? Okay, Ian asks on the chat window, in this first special case, angular momentum is conserved, but would linear momentum of Earth not be conserved because of the force? Absolutely, that's exactly right. Linear momentum is not conserved, angular momentum is conserved. That's right. Because there is a force, if you just consider Earth to be the system, this force will change the linear momentum of Earth. Absolutely. Is there a way of explaining or sort of describing how the linear momentum of Earth changes? Like, can you say that in simple terms based on
direction, but not magnitude of velocity?
Well, it changes both actually, but you're absolutely right. So Earth changes, well, the direction of its motion. It sort of goes around the sun, and just by virtue of the fact that it goes around the sun, well, the velocity is one way at one point in time. It's another way at another point in time. Well, it's kind of the opposite way after half a year, and so on and so forth, right? It's going around the sun in 1 year, and the velocity direction constantly changes, and linear momentum is a vector quantity. So when the velocity changes, linear momentum changes, period. It turns out the Earth has an elliptical orbit, but it's not like super elliptical. It's not very, very elliptical, but somewhat elliptical, I guess. But it turns out the magnitude of the velocity also changes in addition to the direction. So Earth is moving faster, sometimes slower at another point in time. In fact, that's the next example. Okay, so let's say this is the Earth. Like, I've exaggerated the ellipse for the Earth, but it doesn't look this elliptical, I think. Imagine that Earth is going around in this ellipse. This is the sun. Earth, like, it's, let's say, when it's at its furthest point from the sun, let's call that point A. It's still the Earth, right? But we're just calling that point A. And the velocity of the Earth at that point, the speed of that of the Earth at that point A is VA. When it's at the furthest point, like if you say this dotted line is actually the I direction, then VA is going to be the J direction. In other words, the velocity of this Earth is going to be perpendicular to line joining Earth and the sun, because it's going to be tangent to the ellipse, and the tangent here is going to be perpendicular to this line joining SA, okay? So that's VA, and then at its closest approach, let's call that velocity VB, or the speed VB. These positions have certain names. I think furthest point is called the apogee. The closest approach is called the perigee, sometimes called perihelion, I think. In any case, okay, so Can we guess when the speed is going to be higher versus lower?
The speed's the greatest at point B
Okay. Why is that?
because of the gravitational like pulling on it like harder, because gravitation is related to like the distance.
That's right. Yeah. So yes, it's coming closer because of gravitational pull. But so indirectly, I suppose it's certainly due to the gravitational pull. But it turns out that you can sort of think of it as a consequence of, or at least prove this as a consequence of this angular momentum business. Okay. So how do you show sort of quickly that without even considering like how gravitation works and so on, this is just based on the fact that Earth is attracted to the sun by a force that is always toward the sun. The following fact only relies on that one sort of tidbit. There is a force between the Earth and the sun. That force is along the line joining Earth and the sun. It could actually be a repulsive force. You don't even need to assume that this is an attractive force. So this just relies on the fact that this force is called a central force. Central force meaning there's a force that always points to some point, okay? So anyway, so we know that there's a force between the Earth and the sun that's always pointing toward the sun. And because of that, the moment about the sun is 0. Because of that, the angular momentum is conserved about the sun. We can write down expressions for the angular momentum at, let me look at the chat window. A couple of people are saying, yes, it's because the radius of the orbit is smallest. That's right, Nick says, yeah. Smaller distance to sun needs greater linear momentum. So it's going to be angular momentum, not quite linear momentum, I guess, yeah. But yeah, so basically the linear momentum will increase, that's right. Because of this relationship, that's right. But yeah, so angular momentum is conserved. So let's compute the angular momentum here. Let's compute the angular momentum here. And let's equate the two things. So angular momentum here, we're going to use the cross product for the angular momentum. This is the definition, R cross mv. V, the velocity is going to be VA times the J vector. Right, so VA times the J unit vector. R A with respect to S is going to be this distance A times the I vector. So that's going to be this vector, SA. And then we can take the cross product. Do people remember how to take cross products? So these are just constants, constant scalars. So those can come out. And then if you have two unit vectors like this, I cross J is K. And then K cross I is J, J cross K is I, and so on, right? So if you have I, J, K, I cross J is K, J cross K is I, K cross I is J. So it's sort of a circular pattern. I'll write sort of some notes for cross products and post it. But at least for these simple unit vectors, it's just very simple to remember, hopefully. I cross J is K. Okay, so that's MAVA. Similarly, angular momentum at point B is going to be this vector times or crossed with M times this vector. So RB with respect to S is this vector, which is minus BI. And this vector is going to be minus VBJ because it's in the minus J direction. So plug those things in. Minus VI crossed with M times minus VBJ. And then I cross J is still K. The minus and the minus becomes plus. And then we have MBVB. Okay. And then we can equate this angular momentum to this angular momentum. We can cross out the M's, cross out the K's. And we have A VA equals BVB. So that's basically the relationship between VA and VB. If A and B are known and VB is known, VA equals B over A, VB. So VA is basically inversely proportional to A, so to speak. So if A is bigger than B, VA is smaller than VB, right? So like people guessed. So if A is bigger than B, we have B over A, that's going to be less than 1. Something less than 1 times VB gives us VA less than VB. Any questions? Okay, so we've just shown that when it gets closer, the velocity is higher. When it gets further away, the velocity is lower. And it's going to sort of gradually change from here to here. It's going to speed up, slow down, speed up, slow down, so on. Okay. So when we took these cross products, we sort of picked convenient points. Like this point, it's kind of convenient to take the cross product because we have I and sort of I and J, and I cross J was K. So I picked these points so that we can do the cross products more easily. More generally, if you have some random point O, some random point P, basically consider some point P here. We have the line joining S and that point P like this. The velocity itself is going to be tangent to the ellipse. So they're no longer going to be perpendicular. So for these two limits, like for A, this moment arm was perpendicular to the velocity. So basically the angular momentum was just this distance times this distance. Similarly, the angular momentum was just this distance times the mass, of course, okay? Sorry, this distance times this velocity, this distance times this speed, I guess, okay? But if you take some other point here, the two things are not perpendicular. So the cross product is a bit more subtle. So if you take some point P and let's say instead of Q, I'm calling this O. And the velocity of point P is in some weird direction. It's not perpendicular to OP or QP. It's in some weird direction. So what's the cross product, or what's the angular momentum? To sort of do this, it's convenient to break this up into a radial velocity and like VR and V theta if you use polar coordinates, right? So VR and V theta. So VP is VR ER plus V theta E theta. Or if you use the formula from your old polar coordinates, it's basically R dot, which is the velocity or speed in the R direction. And the R theta dot is going to be the speed in the, or the velocity component in the theta direction. So that's VP. And then angular momentum of P with respect to point O, you can use the same formula, or P with respect to O cross MVP. MVP, VP is given by this formula, R dot ER plus R theta dot E theta, or VR ER plus E theta E theta. And you can show that when you take the cross product, this is what you get, MR V theta, or MR squared theta dot K. And that's basically because this R vector is basically R scalar times ER. So this vector is only along ER. So when you take the cross product of R ER crossed with something ER plus something E theta, ER cross ER becomes 0, and ER cross E theta becomes K, okay? So basically you have R theta dot with an M. So that's how you get MR square theta dot, or R v theta times m. That's how you get this. So let's see angular momentum in general. You have to basically take the perpendicular component. This is the r vector. You take the perpendicular component. The radial component doesn't matter, okay, for the angular momentum. Any questions about this? Okay, so those are the expressions for angular momentum, mr squared theta dot or mr v theta. So if you say angular momentum is conserved, basically, well, the mass is just a constant. If you say r is the distance from the Earth, of Earth to the sun, and theta dot is basically rate of change of this angle, or you can say r v theta. So basically r1 square theta 1 dot equals r2 square theta 2 dot. That is basically the implication of angular momentum balance for the Earth, which applies to not just these 2 points, but any point along the ellipse. If you have some theta, if you have some point P and define some theta, then the rate of change of theta is theta dot, then r square theta dot, or r times v theta, which is the perpendicular velocity. That's basically constant. If you take 2 points, 1 and 2, r squared theta dot is equal to r squared theta dot at those 2 points. Any questions? This equation, by the way, I guess we may give you like numerical versions of these things where we'll have a problem with central force and use angular momentum balance to compute, say, given the velocity at one point, what is the velocity at another point, kind of thing, okay? So this equation, by the way, has a very famous name. It's called Kepler's Second Law. Do people know the history of this Kepler's laws, I guess? Why are Kepler's laws kind of important in the history of sort of science and mechanics and so on? Someone says, Saron says it's about planets and stuff. That's right. So I guess Kepler was a scientist from about, I don't know, 500-ish years ago, 450, 500-ish years ago, and was an astronomer of sorts. And he came up with these laws, LAWS, of planetary motion based on observations that other people had made, it turns out, like previous astronomers had made mostly. And he noticed these relationships between sort of the angle it sort of makes with, let's say, the sun and the distance from the sun. He sort of noticed these equations in the data. He was just looking at data and he noticed these relationships and just wrote them down. And they became famous as Kepler's laws, I guess. There were 3 of them. This is the second one of the 3. And then it was a puzzle in some sense. Why are these laws true? Why do planets move in the manner that these laws are obeyed? And then I suppose what happened next was Newton, among other things, discovered the laws of motion, I suppose, the more general laws of motion, F equals ma and things like that, and showed that you can explain, among other things, Kepler's second law and other sort of laws as a consequence of things like F equals ma, right? So it played an important role in the development of the field of mechanics. So someone looked at some astronomical data, wrote some interesting patterns in the data in terms of these mathematical relationships. And then people try to figure out some reason for these laws to be true. And Newton showed that all these different laws are a consequence of this simple equation, F equals ma. And not only the motion of planets arise or are explained by F equals ma, but sort of everything else, I guess. It's kind of the great discovery. Now about 370-ish years ago, I guess it was a discovery around 1680-ish or 1670-ish. However many that is, how many ever years that's ago. Okay, so any questions? So if you have some data and you see some curious patterns in the data, you want to say, why is that? Can you explain it with sort of a more fundamental theory? And that's kind of the source of eventually all sort of great science, I suppose. Usually you see some funny data that you want to explain, and then someone goes about explaining that. Okay, if there are no questions, I guess we shall stop there.